So the usual way I measure this kind of large experimental setup. Our mechanical engineers call this type of accumulators bubblecom or bubblecom reactor. Left side, many bubbles arise and vessel. So this is a bubble flow and blood system. Blood system I invented. This system is carbon dioxide situation into the deep portion of the ocean. So this is fundamental study for practical application of gas system. So these many bubbles containing carbon dioxide. So you can see blue and green beams. This is the beams from laser Doppler velocimeter. So always in my laboratory, in our experiment, we use laser systems. There are many laser systems in my laboratory. So this is wastewater treatment system. We use automation. So the ozone included in the bubble, they active with milk fat and milk protein. So the ozone either formed in the vessel and the bubbles accumulate the ozone like this. So these are very dense form. They dense form as foam at the surface of the vessel. So this system, wastewater treatment system, is really realized and now demonstrated to dairy farms. The one is located in Hamamatsu and the other one is located in Makinohara. So this apparatus plant, the bubble motion is very important. However, to measure bubble motion, in particular, bubble size, bubble velocity, and number density, is very difficult to measure. However, we need it.
Today's my topic is recent development of world-class high-power photonic crystal lasers. But in the beginning, I would like to express my deep appreciation for choosing me this award and providing me to talk here. Thank you very much. And in this work, we are collaborating with Professor Noda in Kyoto University. And today's my talk is consists of two parts. One is high-power photonic crystal lasers, which we developed with Kyoto University, and the other one is some of the application and prospects. And this is the outline. At first, I would like to introduction. This introduction includes the explanation of photonic crystals and photonic crystal lasers, and the next lasing principle and device fabrication process. Then third section is characteristics of our device, and this section I will show you experimental results, and the next the reason of why we can achieve world-class high power. And then fifth section is some of application. At first, I intended to show some application, but due to the time limitation, I just show you one example. And then last, the prospect. let me move to introduction. At first, I will start from the introduction of photonic crystals. Photonic crystal, maybe many people know this word, might hear this word, but this is the periodic structure in which the period are almost same range as the wavelengths of the light. And it enables various types of control of light. I'll show you some examples. This is the types of the photonic crystals, which is one-dimensional, two-dimensional, and three-dimensional. And in my talk, I will introduce the two-dimensional crystals, but the photonic crystal is seen in various forms. This is the examples, the opal, and this is the fabrication process of organic photonic crystals. Very beautiful color are seen. And some of the butterfly's wings have the photonic crystal structures. And these beautiful colors might be caused by the nature of photonic crystal, in which the strong diffraction takes place at special wavelengths and special direction. Therefore, these beautiful colors are seen, I think.
Okay, this is the outline of my presentation. Firstly, I'd like to talk about why we have to control the laser stress in system and how to control it as a background research. And after that, I'd like to introduce two research topics, which is stress engineering for piezoelectric system on the silicon wafer. And I also talk about the effect of the laser stress on the phase transition in the system. And lastly, I will conclude my presentation. And I'm materials chemist, so I'm developing the high performance piezoelectric system for MEMS and for the sensor devices. And now I have to explain, sometimes, as you know, the electrical properties in the system change depending on a lot of factors, such as the microstructure and the interface, boundary, and the laser stress system. And my research topic is laser stress, because the laser stress is a very important factor in determining the electrical property in system. For example, I think this is the most famous, first I have to explain what is the laser stress in system. In general, the laser stress is defined as the sum of the epitaxial stress, thermal stress, and phase transition stress. And first, the rating of epitaxial stress is the lattice speed between the substrate and center. And this factor suddenly released at just the few nanometers. Therefore, we can control this factor. And we also have a phase transition stress. The phase transition stress came from the cell volume change by the phase transition. I mean, this factor is determined by the material, so we cannot control it. So we can control just the thermal stress. The rating of the thermal stress came from the difference of the thermal expanded percent between the substrate and center. So if we design the stacking structure, we can control the thermal stress. So we can control the total laser stress by controlling the thermal stress. This is the philosophy.
So my first result research about biomedical applications before 2011 were retinal prosthetics and compound eye endoscopes and digital dental mirror. I'm still working on the last topic, but they are the examples of the prototype systems. This is a digital dental mirror and compound eye endoscope prototype, and this is a schematic of the retinal prosthetics. So today I'd like to talk about my results. about just retinal prosthesis. Retinal prosthesis, there are several kinds of retinal prosthesis implementations, but one method is to implant silicone chip beneath the retina, like this. Here is retina, and here is special LSI for retinal prosthesis. So light is coming from this direction, and there is a photo sensor, and it converts the light to electric signal. And the image processing is followed. And then based on the light information, light intensity, the stimulator generates stimulation currents. And that is put out from the electrode to this direction. And this current evoke vision. There are remaining retinal cells like this. And in some diseases, not all the cells die, and there are remaining cells. And we can evoke some visual sensation by stimulating some of them. So this is the basic idea of retinal prosthesis called subretinal implant.
First, I explain about spatial resolution limit of conventional optical microscope. This figure shows a schematic diagram of conventional laser scanning microscope. The laser beam is focused to here, and the three objects are illuminated. The focused light is scattered and transmitted. Scattered and transmitted light is detected. The detected signal is added together. The light comes from the three objects. We can distinguish the signal where it comes from. We cannot distinguish these three objects. The spatial resolution is depend on the spot size of focused light. The spatial resolution is given by this equation and is limited to 200 nanometer by the diffraction limit of the light. To overcome this limit, we use an electron beam. This slide explains about generation of nano-sized optical spot. This figure shows a schematic diagram of method to excite nano-sized optical spot. Electron beam is focused to luminescent field. As you know, the focused electron beam, the size of focused electron beam is a few nanometers. Therefore, light emission occurs in the nanometer region. So the optical spot becomes smaller than the diffraction limit of the light.